Good. So let's go ahead and restart. I got some good questions during the break that maybe tell me some additional information I can give to make this a bit more plausible. So let me give one problem that you can work out as a fun exercise, or maybe if you're one of the students required to do exercises, maybe it's less fun. But here's a problem that I think will convince you of what I'm saying about gauging away a flux quantum. Why is this value phi naught special? Okay, so I use this term, and maybe I didn't explain it enough for people who haven't seen it before. So phi naught, I said, it's a flux quantum, which means some quantum of a magnetic field times an area. And one case where this shows up is superconductors. But let's just forget about superconductors. That's where this was experimentally discovered. And let's just talk about what's a little calculation you can do with your quantum mechanics to see why this is special. And again, this is just h over E. Okay, so suppose you take a ring and you just have one-dimensional electron moving, but it's not moving on a line, it's moving on a ring. So we would say, okay, H is P squared over 2m, and I will get that energy, well, it'll be H bar squared K squared over 2m. And the effect of being on a ring is that K is quantized. K will have to be what I wrote over here, 2 pi n over the circumference, which is 2 pi r. So in other words, the fact I was on a ring, that's like periodic boundary conditions, so I quantize K. So now, that problem I think you know how to solve. Go back and try solving it with some flux through a solenoid inside the ring. And this is maybe the simplest demonstration of the so-called Aronoff-Bohm effect. So now, what do you have to do? You have to solve P minus EA, quantity squared over 2m. And you know that A, well, integral of A dl, since curl of A is B, that should be like integral of B dA, which will be phi. So in other words, the fact that I had a phi inside the ring, even if the magnetic field doesn't go out to the ring, what that will do is basically shift the allowed values of K. These are no longer the allowed values of K. They get shifted by a bit because basically before the condition was that when the wave went around, it had to wind by 2 pi n. Now the total winding has to be 2 pi n. There's one part coming from the wave function, but there's also this part coming from A. So I would encourage you as an exercise, basically just go put in an A and solve this problem. And what you'll find is that if you like, this formula is still true, but the allowed values of K have shifted. But then you'll notice something special. What about phi equal to phi naught? At phi equal to phi naught, if you want, what happens to K is that what was n is now shifted over to n plus 1. So at phi equal to phi naught, the spectrum is back to where it was originally. A way to think about that is that what this A is doing is basically inducing a phase shift. As I go around, the boundary condition has shifted from 0 to some phase jump related to phi. But when phi is equal to phi naught, the phase jump is 2 pi. And a phase jump of 2 pi, that's actually the same phase condition I had before. I just shift n to n plus 1. So I'm sorry if that was a little quick, but I think this is the exercise I would suggest you try. Just solve one electron on a ring with an A. And you will see that there's something special, even in one electron physics, about this value, integral of B dA equal to h over E. So then the second thing I wanted to explain, okay, so going over here, let me give the rest of the Laughlin argument, and then I'll say a little bit more about this line I said where conductivity is the same as conductance, because that's actually a clue that maybe things are geometry independent. So let me start with a picture I drew a moment ago. And again, to reiterate, what we're doing now is thinking about a funny way to do an electric field. Normally, if you wanted to apply an electric field, you would just think about putting an electric field in your system. But we know that if you have a time-varying magnetic field, that automatically induces an electric field. So let's think about the time-varying magnetic field. But we know this fact that the spectrum is the same as long as the magnetic field that I'm varying doesn't get out here. The spectrum is the same by the time I get back to n flux quanta. So the picture I was drawing, let me first just draw the lowest Landau level. So I've got energy and mean radius, and this would be in my rotational gauge, m equal to 0, m equal to 1, m equal to 2, m equal to 3, m equal to 4, and so on. Okay, and this would go out to infinity. So now I want to make a model for this ring system where I know there are no electrons at the origin, no occupied states at the origin, and there are no occupied states outside the ring. So let's say I add some V of R, which we call confining potential. Okay, well, we'd expect that that is large here, large at the origin, and it's large far off. So now these states will get moved a bit in energy. Let me draw it this way. So what I've done, again, now I'm no longer just in the lowest Landau level problem, because the lowest Landau level would be exactly degenerate. Now I've added some extra V of R, and it's moved things like this, and maybe I put my Fermi level, let's say here. Okay, so if I say that's my Fermi level, that means to start with, I've got an electron sitting here, I've got an electron sitting here, I've got an electron sitting here, and the others are empty. And of course, in practice, this should be, 1,000 electrons or more. Let's just draw it with 3. Okay, so here's the idea of pumping. And I think maybe the important thing to think about here is we're going to have a kind of transport where the occupancy of the states is not changing. It's the states themselves that are moving. And here's an analogy if you've been to the airport recently, which you probably have unless you're from Florence. So you've probably noticed that if you take your suitcase, say, and you push it down a staircase, then it'll be on the first stair, the second stair. It'll hop back and forth between the different stairs. The stairs stay fixed, and your suitcase falls down the stairs. And that's quite a disruptive process. It's not adiabatic. But now think about when you pick up your luggage from the conveyor belt after your airplane flight, if you checked a bag. Then what's happening there, it's much less disruptive. Your suitcase does not break because your suitcase is staying on a particular step. It's just that the step is moving. So what I claim to you is that this is like the conveyor belt that your luggage comes out on. Because what happens when we apply a flux? Well, all we have said so far is that by the time I get back to, say, 1 flux quantum, the states are the same, which is true. But if I follow that process adiabatically, as I increase the flux, well, think about what that's doing. I've erased my wave functions, but, oh yeah, here they are. My wave functions were like z to the power m, so they had some rotational character around the origin given by m. When I change the flux, I'm basically changing the boundary condition on that, so these are no longer good wave functions for other fluxes until I get back to an integer number of flux quanta. But what happens is that these states just move over. This is sometimes called spectral flow in fancy language. Basically, by the time I've reached exactly one flux quantum through the ring, I've kind of shoveled one electron, where now this empty state moved down there, carrying its emptiness with it, and this filled state moved up there. Just one moment. So now that's empty. Yeah.
Wherever energy comes from, it's like magnetic field.
Where the energy comes from, you mean to make this happen? Yeah. So it's in the thermodynamic limit, it's essentially no energy. So it is an adiabatic process. If you were in a finite sample, you would have some small amount of energy here. But think about this as very large. The point is, in general, for quantized transport, at least for highly quantized transport, like things to be accurate to better than a part in a million, there has to be no energy dissipation. So if you like, this is really a very small change in energy. So practically no energy went in the experimental sample, because these are so-called gapless edge excitations in the thermodynamic limit. If you were doing it in a finite sample, then there's some finite, but it's only at the edges, because these are all basically occupied degenerate states. So if you want, the only energy change was one electronic state got increased a tiny bit, and that's a negligible amount in the limit. And if you're wondering, what's a sign that maybe this is not dissipative? Well, note, normal Ohm's law current is along the electric field. So in this case, the current is perpendicular to the electric field. So in general, a sigma xy does not have to dissipate. So it's consistent with this being a sigma xy, although we haven't quite gotten to that step yet, that here, this is really an adiabatic evolution of the ground state. So other questions? Let me now say why this is at all like a sigma xy. So what this is saying is that in the process of slowly pumping a flux, okay, we don't know at the moment yet how many electrons moved or which way they moved, but at least if I want to get back to where I started, if I want the spectrum after going to one flux quantum to be the same as where I started, then I must have moved some integer number of electrons from a gapless state at the inside to a gapless state at the outside. So in particular, this, and I think this is maybe the importance of the question I was just asked, for this argument to work in the thermodynamic limit, there have to be gapless excitations that the electron can move in or out of at both edges. And these are the famous quantum Hall edge states that we'll have more to say about. But this basically says if there were a finite voltage required here or there, then this wouldn't be an adiabatic process. So it's kind of crucial that at both the inside and outside edge, there's no energy gap.
I'm sorry, but still in this, what is current? Like nothing falls.
Well, I just moved an electron from the inside to the outside, right?
But outside is forbidden, no?
Well, the point is there are these, okay, if you want, think about the last state as it's not strictly forbidden, so I don't have some infinite potential. The idea is I've got some, realistic smooth potential, and if you like, what I've done, okay, so what's the horizontal scale? It's basically one magnetic length. So yes, there has to be a gapless reservoir. I've moved an electron from the inner edge to the outer edge. That's my current. So I haven't, if there were a finite energy it had to reach, then this wouldn't be adiabatic, but it is crucial for this, and it is in fact true about quantum Hall states that there's a gap in the bulk, but there are always gapless edges here, which is where the electron comes from and moves into. So if you like, think about multiplying this by a factor of 1,000 or so, then I will have an edge that looks like, some smooth change in the states. As I make the system bigger and bigger, the amount of energy change is smaller and smaller. So it wouldn't be very physical, I think, to have an infinite potential at the boundary. Then, let me just think about if I've got a finite potential wall, you can actually estimate the velocity of electrons along the edge, and that's my edge state.
But there is no physical current inside as well.
Sure there is. So at least I can say in the process of going from 0 to phi, okay, let me tell you the next thing, and then we can see whether you think it's a physical current or not. what have I done in the process of a flux quantum? So in going from phi equals 0 to phi equal to h over e, so this is we usually think of it as a slow process. It would have to be a faster process if I wanted to dump energy in, but I've slowly ramped up the flux, and that created a small electric field. Suppose NE has been transported from inner edge to outer edge. All right, well, let's ask, what this is saying is that integral of j dt, and let me write it as the total current moving in this direction was NE, and the total electric field was h over e. And what does that tell us about, therefore, the conductance or conductivity? That tells us that sigma xy averaged over the cycle must be n e over h over e, which is n e squared over h. So the point was I slowly increased the flux, and it's a small current because if it took me a very long time to get to one flux quantum, then in that whole time only some finite number of electrons have moved. But if I go back and I ask, what does that mean in units? It means that the average sigma xy over the pumping process was exactly the magic value. So that's my current. So it's a current directed outward. I drove it with an electric field, but now we kind of think that physically, one option is to make a ring and put a flux through it. Another would be just to make a bar and apply an electric field in the bar. But either way, that's an electric field inside the sample. We don't really think it should matter whether the electric field came from this flux trick or just came from applying a voltage. So we kind of think this is probably sigma xy for any electric field we apply. And now one comment, I already told you one special thing about sigma xy, which is that it doesn't have to dissipate. Let me tell you another thing, and just think about Ohm's law for a moment and how it works in different dimensions. So how are sigma and G, where sigma is current density over electric field, G is current over voltage, related in different dimensions? The answer is you can tell that there's something special about 2D, but it's really only special about 2D if you look in the Hall direction, the transverse direction. Okay, so you probably know that in 3D, for example, these don't even have the same units. We would say that the conductance is like sigma times the width of a sample divided by the length. In 1D, the conductance would just be sigma divided by the length. And in 2D, well, now the width is just something with units of length. So I'm saying in 2D, sigma and G have the same units. But sigma xx and gxx have different geometric dependencies because, for example, if I took a sample that was rectangular, I would find it had high conductance in one direction and low conductance in the other direction just because of geometry. But when I look at xy, then I find, well, now, so that here I've been talking about, if I don't put indices, I just mean xx, I mean the parallel conductance or conductivity. But gxy and sigma xy, the special thing here is that it's no longer the width to length ratio. You can find, for example, that these are the same for any 2D rectangle. In other words, you can make a big rectangle or a small rectangle. You can make a fat rectangle or a skinny rectangle. That's maybe a clue that there's something topological going on, which we'll talk about in the next lectures, how to kind of argue that some things about this phase don't really care about the shapes that you're dealing with, much less just the length scale. So this was all one electron. I now want to quickly sketch how you don't need to modify things very much to get the fractional quantum Hall effect. But here, I guess the thing I want to stress is there are only two assumptions that went into this argument, really. One is that whether I apply an electric field with a voltage or with a flux that depends on time is the same physical situation. So the answers for one problem are also the answers for the other, and that's kind of logical from Maxwell's equations. And then point two is the one that I think is not as obvious unless you've thought about it before, but which you can convince yourself from that problem of a ring with a flux through it, which is that the spectrum of the disk with phi equal to n phi naught is the same as phi equal to 0. So note that it is always possible to have a boring insulator. So a boring insulator would be something where if I applied flux, nothing moved over. But that's not the way the lowest Landau level wave functions work, or for that matter, higher Landau levels as well. You'll find that if you put in the flux and you follow how the wave function evolves, then by the time the flux is back to where it started, or sorry, by the time the flux is equal to where it started plus one flux quantum, if you followed adiabatically what happened to these states, they do move over like this. And as they move over, they take the electrons with them, and that's the heart of the integer Hall effect. Now, let me explain what Thouless did. So Thouless, like many others, thought this was, I think, interesting, but wondered, why do we have to come up with this complicated picture, or maybe not complicated, but different picture of how transport works? Why can't I just take what we normally do, which is the so-called Kubo formula, and sit down and compute sigma xy and get the quantization? And the answer is you can, but you need a little bit of new math and topology to understand why. And we're going to do that very soon. But let me first say a bit about what happens if you now think about interactions and the fractional quantum Hall effect, while we've got Landau levels and things like that on the board. So what Laughlin did was motivated by experiment. Some very clean samples have sigma xy equal to, say, e squared over 3h, and some others. You also see 2e squared over 5h. At this point, you see roughly 100 of these other values. Virtually all of them are simple rational fractions with an odd denominator. So we're just going to focus for now on the simplest one. Because, this picture, even if we added interactions or whatever, I guess the point of the argument at some abstract level was in the process of adding a flux quantum slowly, your final spectrum has to be the same as your initial spectrum. That's basically gauge invariance. And because your final spectrum is the same as your initial spectrum, there are only a limited number of things that could happen, and the easiest one is that some number of particles have moved over. But maybe if the particles in your system are something other than an electron, then something else will happen. So the challenge was to think about interactions and to argue that interactions do give you a state where something other than an electron moves over. So let's do that. And I'm actually going to justify the Laughlin state, I'm not going to do what Laughlin did, which is sort of numerical. I'm going to give an argument by Haldane from a year or two later. And it will be fairly quick, because the state is not that different from what we've just learned if we think about what we just learned in a slightly different way. So think about the lowest Landau level, filled with electrons. So now we're thinking about interactions. We should think about many electron wave functions. But if we're thinking about many non-interacting electrons, we would expect to get a Slater determinant of the psi sub m. So what I mean by that is they all have exactly the same exponential factor. So this is just another way of writing the lowest Landau level, except we want to pay attention to particle statistics. We could say psi all right, so I'll have some determinant of, let me write it this way. Let's say I've got particles z1 to zn. Where here the exponents just mean to the power. And this all multiplies times e to the minus sum over I magnitude zi squared over 4l squared. Because the exponential factor I get doesn't care about m. So just to remind you, the point of Slater determinants is this is a trick to make wave functions out of single electron orbitals, and the wave functions will automatically have the property that if I exchange two particles, I get a minus sign, for the mathematical reason that if I exchange two rows or columns of a determinant, I get a minus sign. But there's actually a maybe easier way to write this than to do the whole determinant, which is the following. So the key is, if I think about what are the terms that are going to appear in this determinant, I'll get one, for example, which is like the diagonal. And that means I put z1 in the m equal to 0 state, I put z2 in the m equal to 1 state, I put z3 in the m equal to 2 state. But I'm going to claim that this is exactly the same wave function. Something simpler. So this is anti-symmetric under exchanging two of the particles. And what is the degree of it as a polynomial? Well, I'll have like, for example, in this example, every term in expanding out the determinant, which is some analytic polynomial in the z's, will be one term from the top row, one term from the middle row, one term from the bottom row, which means 1 0th power, 1 1st power, 1 square. So that's n minus 1 times n over 2. Okay, well, let me tell you another wave function with exactly the same properties, and you can check for yourself that it's the same. Let me write this as pi I less than j Zi minus Zj times e to the minus sum over I Zi squared over 4L squared. So this part is the key, and what I'm basically saying is that if I want to, I could think about the Slater determinant of all my rotational gauge wave functions with different m. But here I'm saying, well, let me instead think about it in terms of pairs. So I take any two electrons, and there's one of these Zi minus Zj powers. And maybe the easiest way to argue that this is the same is that these are both completely antisymmetric polynomials of the same degree. So you could ask, how many pairs are there? And this is the number of pairs, and each one of these gives me 1 power of Az. So if you like, for example, the case where I get Z1 to the 0th power would be in every one of these that involves Z1, I always take the other Z. And then the highest power I could get would get the power n minus 1, where every one of these I took, say, Z sub whatever one I'm looking at. So why does this make sense? Well, remember, these are fermions, and the whole point of the Slater determinant was to put in particle statistics correctly. So the wave function needs to vanish when two fermions with the same spin sit on top of each other. And the simplest way, well, it's a polynomial wave function, so the simplest way it can vanish is just Zi minus Zj to some power, and here the power is 1. So that's just another way of writing the filled Landau level. Questions, or are things making sense so far? If you have questions about what I said earlier, that's fine too. Otherwise, I'll just go on. You mean?
We are dealing with a bulk like a rectangular bulk system, and here it is solenoidal, and yeah, why not make sense?
Well, I think maybe the way I would ask the question is, okay, the history of the fractional quantum Hall effect was people a lot writing down model wave functions, and then the real system probably is not having a large overlap with any of these simple models. So we're making a model for the state, and then the question is, what is the universal physics of the state that is true beyond the model, that is true in the bulk? So for example, with superconductors, you could ask the same question. There it started with the BCS wave function, and then we sort of understood later how the truth is more general than that particular wave function. So I think the main motivation for the Chern-Simons theory that we're going to learn later on is that that's sort of true and doesn't require a microscopic wave function. So if you like, what I'm going to do is, okay, so in this case, so far all we've done is rewrite the lowest Landau level. And if I had to take, more complicated wave functions, it's still just rewriting the Slater determinant. What I want to do now is show that at least in a simple model, with interactions, there is a different wave function, and we can argue that it's exact in some limit, and it has an energy gap. And having a gap is kind of the key, because in general, okay, so there will be a field theory picture later on, but if you don't want the field theory picture, here's another reason for maybe when you should trust model wave functions and when you shouldn't. A good reason to trust one is if it has an energy gap that is non-zero in the thermodynamic limit. Because a gap tends to be robust to small perturbations. At least you could say if the perturbation you make to the Hamiltonian is small enough, you won't close the gap. But in general, to prove that a system is in a fractional quantum Hall state or not, there's no simple recipe. We usually wind up doing numerics or something. And in general, the gap tends to be much smaller than the integer quantum Hall case, which means you need samples that have much less disorder. So in other words, there's no proof that any particular magnetic field in a real sample is going to put you in the fractional quantum Hall state. You pretty much have to go out and measure it. But at least we can say, first of all, there is going to be a Hamiltonian, which is what Haldane found, that makes the fractional version of this state the exact ground state. And it has a gap, so there's some stability. And then second, there is kind of a field theory picture where if you ask, if I give you a state that is measured to be in the fractional quantum Hall effect, but you don't think this is the right wave function, how should you describe that state? The answer is you should describe it with the field theory. And that's kind of like if I give you a magnet that breaks symmetry and I ask, well, You know, you have no idea what the wave function of this bar of iron is, so how do you describe the magnetic state? We usually do something like Landau theory, some kind of simple theory of the order parameter. So in general, that's saying that once you're talking about many interacting electrons, in general, you never know the exact state, but you try to make some kind of picture to capture the essentials, and every now and then you can put that into a nice field theory form, like the Chern-Simons theory we talk about. All right, so now interactions. Yes, for the question. No, because each one of these only sees n minus one other particles. So I and j cannot be the same. So if I've got n electrons, there are n minus one terms of this type that it appears in. Well, I've assumed I've only got n electrons. So the point is, if I've got n electrons, then the highest power that appeared over here was n minus one. I'm filling up the first, because remember, m counts from 0. So the first n orbitals are from m equal to 0 to n minus 1. Yeah, we have to start somewhere. So, but now, well, if you think that's fortuitous, let me tell you, what did Laughlin do to win a Nobel Prize? Can anyone guess what the next step is? Doesn't require very much time to write it. He came along and said, when you add interactions, you can get a magical state with fractional particles and even fractional statistics and so on by doing this. So that wasn't a lot of work, but I think why it works and why it has those properties is kind of the magic. So let's do that. So, you know, why is this a plausible thing to do from an energetic point of view? So the idea is, okay, we're going to be in the lowest Landau level. We're only going to occupy 1/3 of the states instead of all of the states. That's what this will do. It will reduce the density. But even more, aside from reducing the density, it means that the wave function vanishes rapidly, more rapidly, when two electrons get close to each other. So here are our challenges. Let's call this psi sub 3 now. Is there an interaction for which psi sub 3 is the exact ground state at density 1/3 of the filled Landau level? And the answer is yes, but I think we'll do that second. 2, does this state, if it is the ground state and has a gap, does it explain sigma xy equal to e squared over 3h? And note, this is not as simple as just e over 3 quantity squared divided by h, because that would be e squared over 9h. So what's going on in that wave function? Well, let's start with that, and then we'll pick up next time. I don't think I'm going to get to my pictures today because I want to finish this, but that's okay. I can start with them next time. They're mostly sort of data and a few other things from the early days of the Hall effect. So how to think about this state before we talk about what interaction makes it exact. So first of all right, in the lowest Landau level, in this rotational gauge, it makes sense that degree of a polynomial c to the m is connected to distance from the origin. as I drew before, as I increase m, these orbitals are rings that move farther out. There's always this same exponential factor, that's important, that keeps things from flying off to infinity. But what I've done here is I've increased the degree by a factor of exactly 3. And a little bit of thinking, you can work out that that corresponds to we decrease the density by a factor of 3. In other words, we have the same number of electrons as without the 3, but they're spread over an area that's 3 times as large. Okay. What is it like now that we know its density? The claim is, and this will come out of finding the interactions, that this is an incompressible quantum liquid, where incompressible means it has a gap, and liquid means it's not a crystal. So, okay, well, we need to talk about energetics and the interaction to show that it has a gap. But it's kind of surprising, because if we just took the lowest Landau level and we didn't have any interactions, then if we filled it up 1/3, there would still be lots of empty states with the same energy. So this gap is different from the gap in the integer case. The gap in the integer case, unless we were at the edge where there's no gap, the gap in the bulk is the cyclotron gap. We have to go up to the next Landau level. Here, the gap has to be generated by interactions. So if we were going to make a picture of what this state with the 3 is doing, well, let's just compare it to the integer quantum Hall state. In other words, filled Landau level. We could think of that Slater determinant we built as though we had a box which was the m equal to 0 state. We had a box which was the m equal to 1 state. And these were all filled with electrons. So now, there's a code. When people write nu is called the filling factor. It means what is the density in units of Landau levels. So this is the nu equal to 1/3 state. Well, we could draw the boxes again, but now they're not completely filled or completely empty. The way to think about them is that they're all filled up with density 1/3. And that's where maybe the liquidity comes in. So it's not like I was occupied, empty, empty, occupied, empty, empty. The mean density in each m you can work out if the system is large enough is 1/3. So now, let's sketch why this is going to give me 1/3, and then we kind of need to show something remarkable for it all to work. And the remarkable thing, maybe we'll wait till next time, but just the idea of what's going on, well, the way pumping worked before was that when I applied a magnetic flux, I emptied this one out. If you want, I pulled down something from the higher Landau level. I moved this one over to there, this one over to there, this one over to there. So these boxes kind of shuffled over, and then maybe this one was empty before because I had a ring potential or something. If I do the same thing here, then it looks like, well, I'm going to empty this out, I'm going to move density over, and I'll have moved density 1/3 out to there, maybe where it wasn't before. So that's why it's e squared over 3h and not e squared over 9h. It's because the single electron wave functions are still the same, and they still get moved over the same way. It's just that when the single electron wave functions get moved over, only 1/3 as much density gets moved over. But there's a tricky part, which is in order to be able to think about transporting charge from the inner edge to the outer edge, we ought to be able to think about some excitation that got moved in this process. So in particular, can I write an excitation of this state with charge 1/3, the so-called quasi-particle or quasi-hole? And that is maybe where this state became quite a shock when it came out. And we can show part of that quite easily. So the claim, this state has fractionally charged quasi-particles. And this is all there, really, in the original Laughlin paper. It wasn't quite expressed in modern language, but it is quite an amazing paper. They're also anyons, which means they are neither bosons nor fermions. So in fact, one point of this mini course is that much of what you learned as an undergraduate was not the whole truth. When you learned that all particles in nature are either bosons or fermions, which is probably the most important, at least one of the most important things you learned as an undergrad, if you have particles that only live in 2 dimensions, it was already known in 1976 that's not quite true. And when we talk about the field theory picture, we'll say a little bit more about that next time. So that's fractional statistics. Fractional charge is easiest to show directly from the wave function. So I'm going to write it, and we'll explain maybe in more detail next time, but I'll write it so you can think about it. Basically, I'm going to make a quasi-hole. Quasi-hole at W, some location in the plane. Easiest to take it at the origin, but let's write it in general. All I want to do is add some factor, product over I, Zi minus W, psi 3. So that seems awfully simple. But let's think about what it did. And maybe the easiest case is to think about W at the origin. So I think I'll maybe finish the details of this next time, but this is maybe the part of this wave function that kind of shocked people, because we certainly knew in physics that you could have quasi-particles that changed a lot of things. So for example, in heavy fermions, the effective mass of the electron is more than 100 times the bare electron. But the charge is exactly the same in Fermi liquid theory. And in superconductors, you get charge 2e, but charge 2e is fairly easy to picture. You bring 2 electrons together, and you get charge 2e. This is saying that in the quantum Hall effect, the electron or hole actually break up into 3 pieces. And why do I say that? Well, it's just a simple argument. What this is doing, this is basically saying, and I'm not adding an electron. I still have n electrons. W is just some point in space. But this term has pushed the electrons away from W. That's why we call it a quasi-hole. And if I ask how much was the electron density reduced, so for example, what we've said is that the density was 1/3 most of the time, but it's depleted in the vicinity of W. And if I ask, well, this is just a matter of degree of the polynomial, how much was it depleted? This object has charge, well, it's a hole, but it's plus 1/3 E. And why? Well, I don't even know if we'll need to do it next time. The idea was just if I compared how much did the degree increase from this compared to the degree increase from adding 1 more electron. Here, the degree increased by 1/3 as much. Which means that the amount of space required is 1/3 of what it would require for a full new electron. So if I want to assign a charge deficit to the region where this object went, it's exactly 1/3. So that is certainly a bit mysterious. But now we have quite strong experimental evidence from so-called shot noise and other things that there are objects of charge 1/3 floating around in these very clean two-dimensional electron gases. And we have increasing evidence even of this maybe more surprising fact, which is that there are statistics other than bosonic and fermionic. So as I mentioned before, there are kind of two threads in topological states of electrons. This is maybe the strongly interacting thread, and we'll have a lot more to say about that, but we'll also have a lot more to say about states of single electrons. And the good news just in the last 10 or 15 years is that states of single electrons turn out to be all over the place in solids. Something like 1/4 of all materials in some giant list of materials may be topological in one sense or another. So at the same time as we're understanding more and more complicated consequences of fractional states, even though they're very hard to measure, we also understand more and more examples of the simpler one electron kind of topology. And I kind of want to try to keep both of those threads going in the next lecture. So I think we have 1 minute for questions if anyone has any. Yes?
So you call this an excitation, but an excitation is like a Hamiltonian. So at this point it's just a wave function, it's just a property, and what makes this wave function better than
That is a very good point. Yes, we haven't talked about the Hamiltonian yet, so it's not clear. And in fact, there isn't a lot of detailed study analytically that one can do of the dynamics of this. Basically, in the Hamiltonian, we'll write down this is zero energy, but it increases the density. When we do numerics, we find, we then put on a potential so it can increase the density, but we do think that even then one has to be careful. Numerics we usually do with a fixed number of electrons, but what we can do is count the number of electronic excitations and say, okay, well, these numbers of electronic excitations make sense if what the electron is doing is putting in 3 quasi-particles that can sit in different locations. So you're right that there is numerical evidence that this is indeed a proper quasi-particle, a stable excitation, but you can't see it from what I told you so far. Good. Other questions? I guess we're 3 minutes over, so maybe you should have your fun.